So, Fugaku is like taking all smartphones sold in Japan and putting it into one room. So that's the magnitude of the machine.
皆さんようこそ. Welcome to Japan Society's Nichibei Global Talks. I'm Joshua Walker. Early in the summer of 2020, Japan's supercomputer, Fugaku, made headlines for winning the title of the world's fastest supercomputer. Since then, Fugaku has also been getting attention for its role in searching coronavirus treatment and effective measures to mitigate transmission. Today, we will explore the world of supercomputers with two of the best experts on this topic. Our guest from Japan is the person who has been a major driving force behind the development of Fugaku. Professor Satoshi Matsuoka is the Director of RIKEN Center for Computational Science in Japan. Our guest from the United States is Dr. Stefanie Chiras, Vice President and General Manager of the Red Hat Enterprise Linux organization at Red Hat, a multinational software company providing open source software products to enterprises. In her previous capacity as Vice President of IBM Cognitive Systems, she was also responsible for promoting practical applications of supercomputers and delivering them to businesses. I can't think of two better experts to engage with than today. Thank you both for joining us today. Let me start with you, Stefanie. For those of us who are not as familiar, could you give us the basics and an explanation of just exactly what is a supercomputer, what does it do, and what does it do for the world, and why is it important? Why are we talking about it today?
Absolutely. And it's great to be here with both of you. So thank you for the opportunity. At a high level, supercomputers are really exactly what they sound like. They're a computing device built to perform at an incredibly high level and able to tackle problems that are outside the boundaries of what standard hardware configurations can really take on, either in terms of complexity or the time to get to the answer, or even both. The promise of supercomputers, though, is that these high-powered, really extreme machines, they can take on challenges that are at the root of what makes all our lives better, whether it's global warming or developing new treatments for diseases. These computers can work through hundreds, thousands, even millions of lines of data in order to get to the root of the problem and get to new insights to help mitigate or even resolve the issue. So the importance here is obvious. This isn't computing to tackle a single business problem or to help us get our taxes computed faster. This is really about using this kind of technology to make all our lives better at a really, really fundamental level.
What about you, Matsuoka-san?
Well, usually supercomputers have two purposes. Why do we build it? And why do we design it? Why do we research and construct something like you see in this background? One is, of course, it's a pinnacle of IT. We design and build these machines, and they need to be incredibly fast and incredibly big and incredibly high performance. In order to do that, you can't just slap together very simple commodity technologies to be able to do it. You really need pinnacle of technologies either to be developed or utilized to basically arrive at a machine like this. So one purpose of building a supercomputer is basically to advance IT as we know it. We advance IT to the ultimate heights. And then we hope that the technological advances we have made will permeate through the rest of the information technology industry. The other reason we build it is, just like Stefanie said, is to basically try to solve problems that are otherwise not solvable using conventional smaller scale machines. And these are usually problems that mankind faces, that the taxpayers who sponsor machines like this are very much aware of and very much concerned, just like the COVID crisis we face right now. So they want these machines to be helping society. So those are the two basically ultimate goals of building machines like this.
Both of you discussed how supercomputers are used to tackle these grand, complex problems that societies cannot solve on our own. COVID-19 seems to be a perfect example. Stefanie, how are supercomputers being used for COVID-19 research, and are there other examples out there?
Yeah, for the most part, supercomputers are really working behind the scenes for many of the things that and I love how Matsuoka-san spoke to it as the pinnacle. Really, those things like space exploration, for example, is often backed by some kind of supercomputer. Many emerging disease treatments also created using supercomputing resources. And various disaster planning and mitigation response, that is like earthquakes or typhoons. Those are mapped using supercomputers. So this is really fundamental mankind issues, as was mentioned. And COVID-19, of course, is a very real and timely example of that. And supercomputers are not only being used to look at vaccines and treatments, but also about the spread and looking at transmission vectors. It may be simple to think that, well, you know, this person is infected and that person is infected, but it's much more than that. It's who did they interact with? What stores did they go to? How many doorknobs did they touch? All of those aspects can be used in order to look at, you know, what is the half-life of the disease and how quickly does this spread? You can do it manually, but it's really time-consuming and super complex. The beauty of supercomputing and its ability to look at just vast amounts of data is that it can extract commonalities across many variables to give us a more generalized look at how the disease spreads. So it's not just that supercomputing is being used to find, you know, what will be the cure, but also it can help us look at how do we limit the spread right now today.
Matsuoka-san, how are you using Fugaku to tackle COVID-19, and do you have other examples?
Well, firstly, you know, COVID-19 has been one of our big early programs that we have instituted. In addition to finding cure, vaccines, also repurposing of conventional drugs and so forth, and also societal elements. The other thing we're doing is to basically trying to find out, for example, if masks and ventilations are effective, because these are critically important. Because we really don't know what somebody coughs, for example. Obviously, there are droplets and aerosols that are emitted from their mouth or their nasal system, but you know they're not visible. So by visualizing how these are actually emitted, and as they transfer through the air, you know, they will dry up. For example, you know, because it's water, so some droplets turn into vapor, and they have very different behaviors. And we've been running many simulations on many types of social scenarios that have basically identified surprising cases of both mitigation measures that are very effective, and some are not. So, and these are being used directly by the government to set up policies to mitigate transmissions, such as classrooms, and also how high the shield should be between the desks, whether you should be wearing a mask, what kind of material the mask should be wearing, et cetera, et cetera. And then, Stefanie and also have been mentioning some really these grand challenge type of topics, but there are some industrial questions, or those questions that are posed by industry that may seem simple, but actually very complex, and also affect the betterment of the society in various ways. For example, how to build better tires. Okay, and tires are extremely complex chemical compound. Also, they have dynamics, you know, because you have treadwear, you have chemicals that allow for the rubber not to harden, but you know it cannot be too soft. So it only takes supercomputers like this to create better tires. For fuel efficiency and safety. There are some examples of creating more efficient toilet bowls, water-efficient toilet bowls. And you think, you know, again, toilet bowls, sanitary equipment, but actually these water-preserving toilet bowls are extremely important in dry countries like the Middle East, where water is much more, I would say, not only expensive compared to oil in those countries, but also takes a lot of energy to create. And the reason for that is it takes a lot of energy to basically desalinate seawater into drinking water, which is wasted by just flushing down the toilet. So again, to save the environment, it's really important to have really water efficient toilet bowls. So, there are many problems they think are mundane. You might think that in a traditional way have been things have been kind of engineered just with human knowledge, but now are being incredibly delicately designed by supercomputers, and that actually really affects society in very important ways.
Matsuoka-san, I'll now start with you to talk about the machine right behind you. How significant is Fugaku's achievement for the future of supercomputers?
Well, I'll try to give you a very short answer, but it's a little complicated. Okay, so of course, we never designed these machines to be, top of the ranking or excel at the rankings. At the end of the day, like I said, supercomputers about, what technology was used to build it and what they deliver in terms of applications. So especially in Fugaku, for various reasons, it was a real mandate to make it, perform well across all applications. So we had this application first type of strategy in building this machine. So, and that was exactly the design goal. However, when you think about, then we have all the benchmarks that try to measure the performance of these types of machines. And just like, the performance benchmark on automobiles, where you measure the acceleration, braking, and cornering, and whether you can step over this hump in the supermarket, or go into a speed bump in the supermarket. When you have these benchmarks, they represent certain facets of limited sets of applications of certain sorts. And so it was a goal not to excel in just one benchmark. Then that would kind of restrict the utility of the machine. But it was a goal basically to have the machine excel in all the benchmarks. And that would really sort of prove that this machine had been, that we have developed is meeting its goals. It's an application first machine. It excels across all application portfolios. And, I'm really happy to report to you that, we became number one in practically all the benchmarks. And and it's very important that we were able to achieve this because this machine, although, has both, there's some collaboration with US and Europe to some regard, but still a lot of design originated in Japan. And we still possess the ability to build these world-leading machines with world-leading processors. It runs the same software as a smartphone or your PC, ARM-based PC. But it's equivalent to about 20 million smartphones in terms of performance. And 20 million is the number, it's about the number of smartphones sold in Japan over the course of a year. So, Fugaku is like taking all smartphones sold in Japan and putting it into one room. So that's the magnitude of the machine. And it's a very amazingly power efficient machine. It's even more power efficient than your smartphones. But being so big, it uses about 20 to about 30 megawatts of power. And what's 30 megawatts? Well, it's about the amount of energy being used by Tokyo Disney Resort. Not just Disneyland, but the entire resort with hotels and multiple theme parks. And we're 24/7. They shut down at night, so we use more electricity than they do. So that's sort of magnitude of the machine we're looking at here. But it's pretty amazing that we can actually build these machines now and run them as a single piece. So, that's how far the technology has progressed.
Stefanie, what was your reaction to the headlines about Fugaku? How is the competition shaping up in the United States, and what does competition look like in the world of supercomputers more broadly?
Yeah, sure. And I think just to touch on a little bit of what Matsuoka-san mentioned, it is such an accomplishment when any nation can claim the world's fastest computer, right? It's a big achievement, whether it's Japan with Fugaku now, but also, of course, last year with Summit in the United States. What's really important, though, is that each generation build upon the innovation of the last generation, that this really becomes how do we make the whole space of supercomputing better, stronger, faster with every generation that comes out. And Fugaku this year is a big step forward, particularly in showing artificial intelligence and machine learning as an algorithmic tool in supercomputing. And also, as was referenced, it is what's called, it's built upon silicon architecture that is ARM-based, right? Which is a uniqueness. It's one of the first supercomputers to be built on ARM-based architecture, and ARM-based is generally used in your smartphone and others, so it's quite a unique use of it. And While building on non-x86 architecture in the silicon, that's not new. Summit and Sierra back in 2019 were built upon IBM Power Systems. But what is new is that this paradigm that Fugaku has around modularity and standards-based design, amazingly powerful at scale with Fugaku, but it can be stepped down into corporate data centers and smaller laboratories. So this is really important because it's not just about Fugaku's kind of being that pinnacle for supercomputing, but being that pinnacle for what can be done in computing at large. And as was mentioned, we're incredibly proud that it does run Red Hat Enterprise Linux. This was a great collaboration for us as well. And in fact, since Linux has been kind of this platform for innovation. Since 2017, every computer on the top 500 list has used some form of Linux. And so that's a big push because it's not just about the performance of why Linux is used. It again comes back to that standardization. It's that Linux is understandable. It's based upon common standards. It's the same thing that's running and the scientists are running on their desktops and in their workstations, and that makes it pervasive.
Dr. Matsuoka, you mentioned a little bit about your collaboration with the United States in Fugaku. Are there other examples of US-Japan collaboration that we should know about?
Well, over the past 10, 15 years, the US-Japan collaboration on supercomputing has really been has flourished and enriched predominantly all the centers in the U.S. and all the centers in Japan. There are lots of collaborations going on, not just in terms of the actual machines themselves, but the application and software, and also people exchange and so forth. Because we recognize one of the things we recognize in this era, like Fugaku and the upcoming U.S. machines, which basically exceeds the last generation machine by several fold. These are so-called exascale machines, or machines that are able to perform 10 to the 18 operations per second, and 5 to 10 times faster than previous generation machines. When we started planning for machines like this back in around 2008, 2010 timeframe, it was painfully recognized that it was going to be one of the biggest challenges that the community will be facing. And we can't really go at it alone. We really need to collaborate. We need to exchange ideas. We need to exchange artifacts like the software and other ideas, and applications and other ideas in order to achieve the goal. And and even before that, the word collaboration. But I think this aiming for this next generation machines that everybody recognized would be, like the moonshot type of R&D, basically helped the U.S. and Japan community to bond together quite tightly. So, like you said, there are some technologies that are actually being used here. Fugaku, the processor, is being reviewed by U.S. labs to see if it's viable in their own ecosystem. And we expect that we would have a cross-utilization of these machines in some ways. We're already doing that for COVID, but also cross-utilization in terms of using the machines to design the next generation, even the next generation, which will even be harder. So there is competition, yes, but I think it's a very, very friendly competition in the sense that we're heightening each other for the good of mankind. We're exchanging info. There's very little secret, and it's been the results have been really outstanding because of that.
Yeah, I think supercomputing and scientific and academic research, they're really intimately tied as we tackle these problems. So when I look at how we move forward, the fascinating thing and the really inspiring thing about looking at how supercomputing is advancing and how we do kind of work together in this friendly competition with a shared purpose is it really takes all the innovations that are happening, whether it's in the hardware aspect, whether it's in the software aspect, or honestly, whether it's data. And I think one of the things that we're seeing here is the pull together and the the pinnacle, coming back to that word, because I really like that word, is taking the best that can be done in the hardware, the software, and the available data, and using that as the next step forward. And data is everywhere. As we combine, I'll use COVID as an example because we've talked a lot about that, right? Sharing data, using that data into the supercomputers to make sure that they're getting the best insights that we can all build upon. All of that sharing is really key. I think moving forward, as we look at, academic researchers working together, they will all share some amount of the technological record. And the research and workloads running on supercomputers, I think you'll see both hardware designs, software innovations, right? Certainly we believe in open source. That is pushing forward the next envelope of innovation. And then pulling together vast amounts of data, that's what's going to allow us to tackle these problems in mankind in a whole new way. And clearly the ARM-based design of Fugaku in general is something that will continue to be iterated upon and drive both the humanity level challenges, also some of these critical corporate challenges, but there's so much more to be done. This is what I find so inspiring about this area.
Thank you. I'm inspired by both of you today. I have one final question. If you could leave one message for the future generation to look back on this moment in time, what would that be? Let's start with Stefanie and then Matsuoka-san.
I think one thing that we believe strongly in is that collaboration fuels the best innovation. And having a shared purpose, it's the vision of why we're doing what we're doing. And I think Matsuoka-san started there. It's why do we build them? What is the questions we're all trying to answer? And the goal is for all of us to stay focused on that. Yes, we will work to make each other better, but it's the shared purpose that will unite us, and collaboration will drive the best out of all of us.
Well, it's just like it took the U.S. 10 years from the Kennedy speech to actual Neil Armstrong landing on the moon, 10 years. This machine, from its inception to now where we are now, all built, it's taken 10 years. It's been a very long effort, lots of collaboration, as I mentioned, not just by small sets of people, but the entire Japanese community of HPC, as well as collaboration with the U.S. that resulted in this machine. The reason being that we had set this amazingly high goals, which are not attainable by a single entity, but only possible through this global collaboration. The entire community of Japan, also in collaboration with our partners in the U.S., that allow for this machine to be constructed. Otherwise, we would have some machine that's 3 times bigger and 3 times more expensive, which would have not been a very good machine to work with, or of course we'd not be able to afford it. So setting high goals, I think, especially in large projects like this, is very important. Goals, again, that seem unattainable, only attainable through these collaborations, and then actually working out how to achieve the goals given this enormous target. That's something I think the next generation should really think about. What's going to be the next big goal? And then what would be like a national level or even international level collaboration to achieve that? So think about, and that'll be sort of like a dream project, and really like people, the younger generation to think about that. Not, really think about problems we're facing tomorrow, but really, what we would be doing in 10 years and actually achieve them.
いかがでしたか? We hope you enjoyed this Nichibei Global Talks. For me, the takeaways were interesting. Dr. Chiras and Dr. Matsuoka illustrated the greatness of supercomputers, how significant they are as the pinnacle of IT and advancing IT in terms of their application. Supercomputers help tackle mankind issues that are beyond the scope of standard machines. From COVID-19 to climate change to space exploration to disaster preparedness, planning, and mitigation responses. It was fascinating to learn about all the examples of how supercomputers help industries address seemingly simple and mundane, but ultimately complex and important questions. How to make it better, how to make better tires, how to make more water-efficient toilet bowls. It was a real treat to hear firsthand from the leading people behind the development of the world's now fastest supercomputer, Fugaku, about its scale and its achievement to work across applications that also run on our smartphones. We at Japan Society are proud to see that there's a Japanese supercomputer on the top for now, but we're equally proud to see how such healthy competition between the United States and Japan has heightened each other in terms of research and development and sharing data and building on each other's achievements towards a shared purpose. Please subscribe to our channels and follow us on social media to stay connected. Thank you again and see you soon. Mata o ae shimashou!